All right, so 708, numbers 1 to 4, and they're all to do with the calcium atom. So calcium drops from 5.16 electron volts above the ground state to 2.93 electron volts above the ground state. So its initial energy level is 5.16 electron volts, and its final is 2.93 electron volts. And the question wants to know what is the frequency of the photon emitted. So first we have to find the energy of the photon, so final minus initial. So EP is equal to 2.93 electron volts minus 5.16 electron volts. And you're going to get a negative here because it's being emitted. 2.23 electron volts, the negative just means emitted. So we need to switch this to joules in order to be able to find the frequency, right? Because we want EP is equal to HF, so F is going to equal EP divided by H. So you can drop the negative because we know it means emitted, and you're going to divide by 6.626 to the negative 34 joule seconds, but you can't have electron volts up there. So you need to multiply by 1.602 to the negative 19 joules per electron volt. Now you'll be in joules, and you get a frequency of 5.3916 times 10 to the 14th hertz. Number 1, completed. Number 2 says, calcium atom is in an excited state when the energy level is 2.93 electron volts. So 2.93 electron volts above and that's E2, above the ground state. A photon of energy 1.2 electron volts, so EP 1.2 electron volts, strikes the calcium atom and is absorbed by it. To what energy level is it raised? So EP is equal to EF minus EI, and we're looking for EF. So EF is going to be equal to EP plus EI. So 1.2 electron volts plus 2.93 electron volts, and you end up getting an energy level of 4.13 electron volts. But the question actually wants to know what level is that, so now you need to look at the diagram and you'll see that it's E3. Okay? If you didn't have the diagram, there'd be no way you could answer that one. It's different than hydrogen where we could figure out the different energy levels, but in calcium we need the diagram because Bohr's equation doesn't work. Number 3, a calcium atom is in the excited state at the E6 level. Okay, so E6, and then it's going, how much energy is released when it drops to E2? So it's going from E6 to E2. Okay, so EP is equal to final minus initial. So EP is equal to, final was E2 minus E6. E2 we had already looked up, it was 2.93, I believe, electron volts, right? And 6 is 5.16, so minus 5.16 electron volts, and so you end up getting negative 2.23 electron volts, where the negative means it's emitted. Number 4, I think that's all the 3 asked. How much energy? Yeah. Number 4, a photon of orange light, wavelength 600 nanometers. Okay, so we're going to be able to find the energy of the photon from this, but first, enters a calcium atom in the E6 energy level. So E6, which we already looked up, was 5.16 electron volts. And ionizes the atom. So now if you look at the chart, you'll see the ionization energy, the level, is 6.08 electron volts. So we can figure out how much energy does it need to be ionized, right? So the EP we're going to find here is really like the work function when it's in this excited state. So final minus initial. And so it'll be 6.08 electron volts minus 5.16 electron volts. So when you do this, you get 0.92 electron volts. And like I said, this is kind of like the work function of that particular electron, how much energy that particular electron needs to be needs before it'll be ionized. So it's the ionization energy. Okay, so now the question wants to know, if this wavelength of light is absorbed, how much kinetic energy will the little electron have when it's given off? So first we need to find the frequency. E is equal to HF. First we need to find the frequency. C is equal to F lambda. So F is equal to C over lambda. So 2.9979 times 10 to the 8th meters per second over 600 nanometers. And you end up getting F to be 4.9965 times 10 to the 14th hertz. Now you can find E with that. So E is equal to HF, so 6.626 times 10 to the negative 34 joule seconds times this 4.9965 to the 14th hertz. And you get an EP to be 3.31068 times 10 to the negative 19 joules. Of course, if we're going to do anything with it and the 0.92 electron volts, we need to change it to electron volts. So divide by 1.602 to the negative 19, and when you do, you get 2.06659 electron volts. Okay, and so now we go to our photoelectric effect equation again, because it wants the kinetic energy. And so it's going to be the HF of the light coming in minus the energy that the electron needs to be freed. And so it's going to be the 2.06659 electron volts minus the 0.92 electron volts. And when you do this, you get an EK max to be 1.1466 electron volts. And did it ask for it in electron volts or joules? It doesn't say, so we can leave it in electron volts. Okay, so there were your homework questions.